Hi everyone, welcome to my video number 4. It's about double integral in polar coordinate. Double integral in polar coordinate. I'm not sure, but I think you have made this term before. So what is polar coordinate? Normally when we integrate over the circular region, for example, so we need to use polar coordinate to make our life easier. Yeah. So if we want to evaluate this function f xy dA, where your region is R, where R could be of the form, say, a circular, any form of circular. For example, if you have let's say this is your region, this is your R, that, okay, or you might have something like that. This is your R. Okay, so for example, you have this kind of region. This region, let's say the radius 1. So you have this equation is x squared plus y squared equal to 1. If we use double integral of xy in rectangular coordinate dx dy, which means you need the limit of integral here, limit of integration there. You need to put this the limit from for x from -1 to 1, from -1 to 1. Yeah. But for y it's quite complicated because you need to consider to write that function in term of x. So which means you have y is plus minus square root 1 minus x squared. Okay, so then the negative part here, the negative part we put down here, then the positive part you put it down there. Okay, so this the lower boundary given by y is negative square root 1 minus x squared. The upper boundary give you y equal to positive 1 minus x squared. So we need to use that function as a limit of the integration for this integral. So it's not easy, because when you plug in, after we do the integration and plug in, then you in that integrand you may have the term of that kind of terms, which is not easy to evaluate. So to overcome this problem, we have what we call we transform from the rectangular coordinate. This is what you have, rectangular coordinate, to the polar coordinate. Okay, so this is rectangular coordinate to polar coordinate. So what is polar coordinate? Polar coordinate is we deal with radius of the integral, that r, and the angle. So as you can see here, any point, if this is x and y in rectangular coordinate, any point on xy, let's say if you say here, this point can always be represented by r and theta. Okay, so for this kind of transformation, what we need, we have x is equal to r cos theta, y equal to r sin theta. Then of course r is given as x squared plus y squared is given by r squared. Okay, so this is the main um, features when we do the transformation from rectangular coordinate to the polar coordinates. Apart from that, we have to bear in mind that in the polar in the rectangular coordinate, if let's say this is our region, if you take a part of it, of that region, all right, so this is dy, this is dx, so the small um, area is given by dx and dy. Delta x, sorry, delta x should be delta x, delta y, so this is delta, sorry, delta x, delta y. Okay, so when we do that transformation, remember that this small area here might change to something like small area here. All right, so it means we cannot simply those area written as dr d theta, cannot. We must have something in order to balance out the area for the rectangular and area for the polar coordinate. So those, in order to make those area equivalence, so we need to put something that what we call Jacobian. The Jacobian of the transformation. Okay, I think you know the Jacobian in the function of multivariable. We have you have seen the Jacobian, what the Jacobian is all about. Now in this case we have a function of xy. We transform into, look at that, x arc to arc cos theta and y to r sin theta. So which means our function of fxy now become r cos theta, r sin theta. So what I did here is just transform x into r cos theta, y into r sin theta. Okay, now for this integral over the region R, f xy dx dy. So if you do such a transformation, under this transformation, we're going to have, okay, we integrate over a new region. Let's call that L1, R1 for example, a new region, R1. So new region here means that we, after doing the transformation, and then f of r cos theta sin theta, okay, and dx dy here, as I mentioned here, this delta x delta y dx dy, we need to have some coefficient dr d theta. So we have here the Jacobian dr d theta. So in this transformation, what is the Jacobian j? So we need to determine what is j. Okay, so the Jacobian is given as, I think you know this thing, this is x, a function of r and theta, y is function of r and theta. So Jacobian, we have x r x theta, y r y theta. Okay, so if you do this, what we have, xr is cos theta, x theta is negative r sin theta, yr is sin theta, and y theta is r cos theta, Okay, you solve this. What is it? This is r cos squared minus you got plus arc sine squared theta. So you can factor out arc. What left is cos squared plus sine squared, which give you 1. So everything you got arc. So the Jacobian in this transformation is given by arc. So therefore the integral over fxy dx dy under polar coordinates can be written as, let's say, r to r1, your fx r cos theta, y sin theta, this is r sin theta, r dr d theta. Do not forget that. Okay. Let me give you an example of how to use this. Okay, so example, let's say we want to evaluate r 3x plus 4y squared dA where R is given as the region in the upper half plane bounded by x squared plus y squared equal to 1 and x squared plus y squared equal to 4. Now look at the region. If you look at this region, this is a circle of radius 1, this is the circle of radius 2. So if you plot this a little bit or sketch a little bit, so we have a circle of radius 1, okay, and you have a circle of radius 2. So this is our region. Alright, this is x squared plus y squared equal to 4. This x squared plus y squared equal to 1. So the limit here, this is 1, this is 2. And of course your r is, if you consider this is your r, theta, that's your r. So as you might expect, because our region is in circular form, all right, so we need to apply the polar coordinates. So how to do this? So our r, basically, if you look at from there, our r is given as, look at from there, it is a half circle. We have a upper half plane, so we exclude that part. Okay, we exclude that part. We only have that part. So our theta, so all r and theta, all r theta, such that, okay, your r between 1 and 2, and your theta between 0 and pi, because this is only half of circle, so 0 and pi. Alright, and then now we want to evaluate this r 3x plus 4y squared dA. Your dA in the normal form or in the Cartesian coordinate or in rectangular coordinate, this is, we have 3x plus 4y squared dA is dx dy. But by looking at the region that we have, dx dy we have to transform into polar coordinate, so we have the Jacobian there. So that expression can be written as so your r now is given by that. So we can use this r from 1 to 2, okay, and theta from 0 to pi. You substitute those, x is 3r cos theta, substitute those plus 4 y is what is it, we have x r cos theta, y is r sin theta. So y squared, so we have 4 squared sine squared theta, dx dy transform into r dr d theta, where r is the Jacobian. I have shown this earlier. Okay, so what left is just we just need to evaluate this. All right, we evaluate over r, and then we evaluate over theta. So I think you can do this. Can you? So let's try. I won't solve this in detail, pi, because this is just a normal integral that you can do it. So we have here is 3r squared cos theta plus 4r cubed sine squared theta. Alright, so dr d theta, we integrate with respect to r first. So we have integrate theta from 0 to pi r, so we have r cubed, cancel out with that 3, so we have r cubed cos theta plus that one is r4 cancel out, so r to the 4 sine squared theta, your r from 1 to 2 d theta. Okay, so solve this. So what we have, integrate 0 to pi 2, you have 8 cos theta plus 2 to the 4 16, right? 2 to the 4 16. Yeah, that's 16 sine squared theta for 1, so you have cos theta plus sine squared theta d theta. Simplify that, so what you have, cos 7 cos theta, that one is plus 15 sine squared theta, integrate from 0 to pi d theta. Alright, to evaluate this, you cannot simply write sine squared theta d theta, this is one cos don't do this, this is wrong. Okay, you need to use identity. So what is it? Sine squared is a half 1 minus cos 2 theta, then you can evaluate. So I think you can do the rest. This is the final answer is 15 over 2 pi. Okay, And then I have one more example. I can give you one more example. This example quite easy. All right. So example number 2. Another example. So let's say we want to find the volume. Again, the volume of a solid. Bounded by plane z equal to 0. All right, bounded by plane z equal to 0, and a parabola. The parabolic z equal to 1 minus x squared minus y squared. Do you recognize this form? If you look carefully on for z equal to 1 minus x squared minus y squared, if we have z equal to 0, which means this is on xy plane, we're going to have x squared plus y squared equal to 1, which is a circle. All right. So as getting bigger, because we consider a positive part, y positive, because we consider that solid bounded by, so we consider the positive part. So basically we have something like this is in 3 dimension. On xy plane we have a circle that, and look at this, it goes like this. All right, so that's your, so this is your arc, and this is the whole region, the volume that we are looking for, and the volume that we're looking for. Okay, so to evaluate this, we just need to evaluate over the integrand over the surface with the region R. So volume given as, we integrate over those R. I use R region, and our F. Remember that our F. This is our F. Okay, this becomes our function of xy. Yeah. So 1 minus x squared minus y squared dx dy. Okay, this is not easy again. So, but look at those regions. If we transform, we just consider on xy plane. If you consider xy plane, your R is just a circle of radius 1. So you just need to transform all those things. We have because of that circle, we have x. We can use this x cos theta, y r sin theta, and remember that dx dy is r dr d theta. Okay, so substitute into those. So what we have, this is equal to theta from 0 to 2 pi. Why 0 to 2 pi? Because we have from 0 to 2 pi, a full circle. And your r from 0 to 1, from your r is from 0 to 1. So if you simplify this that part, you have 1 minus x squared plus y squared. Using that transformation, this will give you r squared. So you have, there is 1 minus r squared. So substitute that. So we have 1 minus r squared, and dx dy is a r dr d theta. Okay, and then you can just simplify this. You have pi over 2. The rest, the small thing, you do it. All right. I think that's all for this video. Quite long actually. Thank you.